Characteristics of induction motor. The operation of the three-phase induction motor is discussed thoroughly in this unit. The torque equation and its maximum interrelationships between the starting, running, and the maximum torques are derived. As in the case of a transformer, the equivalent circuit and the phasor diagram can be developed. This will enable us to understand the performance characteristics in a simple manner. Special induction motors such as deep bar and double case, which give high starting torques and better operating characteristics, are also introduced. Special features like crawling and cogging and methods to overcome these defects enable us to modernize and develop three-phase induction motors, which will give excellent operating characteristics. Torque equation. The torque development is proportional to the power transfers to the rotor of induction motor, where T is the torque, E2 is an induced voltage in the rotor at standstill, rotor speed is 0. I2 is the rotor current. Cos phi2 is the rotor power factor. Under the running conditions, induced DMF equal to SE2, where S is the slip ring. Rotor reactance equal to SX2, where X2 is the standstill reactance. Power factor equal to Substituting the power factor in equation 1, the torque is given as starting torque. Torque obtained is, where TST becomes the starting torque by substituting S equal to 1. Therefore, condition for maximum starting torque. Taking R2 as variable and differentiating TST with R2, the equation is given as. On simplifying, the condition for TST to be maximum is obtained R2 equal to X2. The starting torque is maximum when the rotor resistance is equal to the standstill reactance. Condition for maximum torque under running. Treating S as a variable and differentiating Tx's in equation 2 with S and equate to 0 yields. On simplification, the condition for the T to be maximum is obtained as. The running torque is maximum at a slip given by torque equation, maximum starting torque. Substituting the value of slip S equal to R2 by X2, the equation for T maximum is given as. Since E2 is nearly constant, T maximum is inversely proportional to X2. The maximum torque developed is inversely proportional to the standstill reactance of the rotor. T maximum is also called the braking torque. It is inversely proportional to rotor standstill reactance, since for a given motor E2 is constant. When the load is such that the induction motor has to develop a torque more than T maximum, the motor comes to rest. Torque, slip characteristics. The torque versus slip characteristics is a very important graph. It is plotted as shown in the image. The following are the inferences of induction motor from the curves. As R2 increases, the TST increases. At n equal to 0 or s equal to 1, TST is maximum if R2 equal to x2. The working range of the motor is hatched. The range of slip is from 0 to 0.05. When S is more, the rotor copper loss will increase. Rotor copper loss equal to rotor input into slip. Therefore, higher values than 0.05 are not preferred owing to increased copper loss. The braking or maximum torque is far away from the working range. It occurs at a slip S equal to R2 by X2, which is generally higher than the working slip. At higher values of slip, where the slope dt by ds is negative, induction motor will not be stable. Because if dt by ds is negative, it means that when torque increases, slip decreases. But in induction motor, what takes place is, when the load increases, the slip also increases. Hence dt by ds is positive. This is necessary for stability. Therefore, in the region left to the point S equal to R2 by X2 on the torque slip characteristics, the motor is not stable. Behavior at normal speeds, near synchronous speeds. When S lies between 0 to 0.1 as shown in the graph, it is nearly a straight line. It is noted that as t increases, slip increases from the equation 2 as shown in the image. For low values of slip, s square into x2 square is small compared to r2 square, hence t is proportional to s. Under normal working conditions, when the slip is quite small, the torque is directly proportional to the slip. Behavior at lower speeds, speeds much lower than synchronous speed. At speeds much lower than the synchronous speeds, s square x2 square is far larger than r2 square. The equation can be written as: at low speeds, the torque of induction motor is inversely proportional to the slip. Interrelationships of starting, running and maximum torques. Torque is important in the case of any motor. So in respect of the three-phase induction motor, which is the most commonly used motor in the industrial world, starting torque is also very important. In some practical cases like electric cranes, elevators, sawmills, etc., starting torque is more important. These motors must be heavily loaded before starting. In some motors, they are first started at no load and then only the load is applied. Such motors can have relatively less starting torques. The braking torque is also important to all motors, as the motor abruptly comes to stop if the load disturbance occurs even for a small time due to external factors. To prevent such cases, the running torque should have a wide margin from the maximum torque. Keeping these points in view, the interrelationships of these torques are derived as below. Full load torque and maximum torque. Starting torque and maximum torque. Click each tab to learn more. Full load torque and maximum torque. From equation 2 for a full load slip of SF. From equation 3. Starting torque and maximum torque. From equation 2, putting S equal to 1, the equation is given as Equivalent circuit and phasor diagrams. Similarity between induction motor and transformer. The transformer and induction motor have some similarities, which have been noticed earlier. In both the cases, the mutual induction plays the key role. Transformer has a primary and secondary, whereas the stator and rotor in the induction motor. The secondary is connected to a load which draws electrical power in transformer. But in the case of an induction motor, secondary or rotor is short-circuited. The frequency in it is SF and the electrical power is converted to mechanical power. The similarities and differences between the two are shown in the table. Keeping the above points in view and the equivalent circuit of the transformer, the equivalent circuit of the stator of the induction motor is as shown in the image. The stator of the induction motor is represented by an equivalent circuit as shown in the image. Note the similarity between the primary of the transformer and the stator, where R1 is stator resistance per phase, X1 is stator reactance per phase. R0 is the shunt resistance, which represents the iron loss in the stator core. Its reciprocal Z0 equal to 1 by R0 is called conductance. X0 is the shunt inductive reactance, which represents the magnetic current I mu. Its reciprocal B0 equal to 1 by X0 is called susceptance. V1 is applied voltage to the stator. When the motor delivers no power output, the input is equal to the stator losses only. No load current equal to I0, where IC is core loss component. I mu is magnetic component. On similar lines, the equivalent circuit of the rotor can be developed. Note the similarity with the secondary of the transformer. Equivalent circuit of the rotor. The rotor may be represented by the following circuit. Dividing both the numerator and denominator with S, it is given as the resistance term R2 by S could be split into two parts. The first term R2 is rotor resistance. The second term represents an equivalent resistance. For Pm equal to mechanical power developed. When I2 flows in it, its copper loss is. From the interrelationships of losses, Pm equal to mechanical power developed. Therefore, the equivalent circuit of the rotor is shown in the image. If the turns ratio K is K is equals to N2 by N1 is equals to number of turns per phase in rotor by number of turns per phase in stator. The rotor parameters can be transferred to the stator as in the case of a transformer. Then the exact equivalent circuit can be obtained as shown in the image. In the equivalent circuit, rotor resistance transferred to the stator equal to rotor reactance transferred to the stator equal to. As in the case of transformer, the shunt admittance branch can be shifted to the left extreme without committing much error. Then the approximate equivalent circuit can be designed as shown in the image. maximum power in synchronous watts and maximum mechanical power development. The approximate equivalent circuit is drawn as shown in the image. Power developed in synchronous watts in the rotor input power is given by torque developed in synchronous watt equal to rotor input equal to rotor copper loss by S equal to cross output power into Pm by 1 minus S equal to Pi.